Okay, let's talk about the operation of dilation. It happens on the space of polynomials. I'll give you its definition first. Given a polynomial p of x, for example x squared minus 1, substitute 2x minus 1 in place of x, form a composite function where every x is replaced with 2x minus 1. That's the operation. It actually finds tremendous applications in wavelet theory. And Gilbert Strang has a book on that topic as well, which is basically shows that wavelets can be thought of as an application of linear algebra. A wonderful topic and a beautiful theory, and really shows off the power and the limitless efficacy of the linear algebra perspective. Okay, so that's the transformation. I'll give you a couple examples in just a moment, but I just want to address the word geometric. So would the word geometric apply here? So here's the transformation. It happens on the set of polynomials, and I'm again inviting you to accept these objects, polynomials, on their own terms. What are polynomials? You can think of polynomials as expressions in x. They can be added together to produce another expression in x. They can be multiplied by a scalar to produce another expression, or form linear combinations. So you can do the two sorts of things that you need to do with objects in order to call them vectors. So polynomials are vectors. This operation, this is a linear transformation. It treats polynomials as vectors because the only thing that's important here is the ability to add them together and multiply them by a number. That's what makes them vectors in the eyes of linear algebra. So we can once again ask the question of eigenvalues and eigenvectors of this transformation. In fact, that is the question I'm asking. What are the eigenvalues and eigenvectors of this transformation? You may not know now, you will in about 5 to 10 minutes. And again, I could almost use the word geometric. Whenever you accept objects on their own terms and treat them for what they are, in this case, they're just polynomials. You don't think of them as, if they're quadratic polynomials, triplets of numbers or anything like that. You just accept them for what they are. I tend to call that perspective geometric, when you accept objects for what they are. So it's not geometric in the sense that they're pictures or lines or geometric vectors. This is really, maybe invariant is a better word. Right? This is, what I'm emphasizing here is that we haven't yet chosen a basis. We haven't yet converted these beautiful objects into sets of numbers and started applying algebraic methods to them. So from that point of view, it's geometric, but it's not geometric in the sense that geometry is involved. So I would submit that geometric is not a good word. So use the word invariant or on their own terms. So, accepting polynomials on their own terms. Can you tell me the eigenvalues and eigenvectors of this transformation? Let's see, maybe we can guess a couple. Let's, just for practice sake, apply this transformation to x squared. So the rule says, once again, the game is played by the same rules. I give you the transformation, the rule, and then you apply it. So I have to specify the transformation, which is what I did here. So the rule is, whenever you see x, plug in 2x minus 1. So x squared goes to, imagine 2x minus 1 squared, goes to 4x squared minus 4x plus 1. That's what this linear transformation does. Completely unintuitive. If you were to draw the graph of this next to the graph of this, maybe you'll see what it does and why it's called dilation. Let's do it for one more. How about x? X, well, x goes to 2x minus 1. That's easy. Any of these eigenvalues, eigenvectors in this context called eigenfunctions. Eigenfunctions is a good word if your totals, what's the word? If you just want to overemphasize the linear algebra perspective, you would call them eigenvectors of the linear transformations. Linear transformations have eigenvectors. but acknowledging the true nature of these objects, eigenfunction is the better word. Are any two of these eigenfunctions? They aren't. This is not a multiple of this. This is not a multiple of this. So we don't yet have eigenfunctions. Can you think of the eigenfunctions? Not so easy, by trial and error. I think there's one that's kind of evident. Well, let me first ask you this question. What about d of x squared plus x? Well, it's by the very nature of this transformation being linear, if you add up the inputs, you have to add up the outputs. And the answer is 4x squared minus 2x. That's it. Right, once again, not an eigenfunction. I think one eigenfunction is relatively easy to guess. Here it comes. D of 1, the polynomial. It sends 1, 2, whenever you see x, plug into x minus 1. There are no x's, so it just becomes 1. So there you go, that's an eigenfunction, and 1 is the corresponding eigenvalue. Now if you just limit your attention to quadratic polynomials, can you guess two more eigenfunctions and two more corresponding eigenvalues? I don't think I could. So this is a wonderful example. So you can tout the geometric perspective all you want, but I think the lesson is to not be so, I keep looking for the right word, just so devoted to one method to the exclusion of others. If you love some approach to pieces, an even more effective way to live would be to continue loving that approach to pieces, but to embrace the fact that there are other approaches, and you should really be obsessed with having as many tools in your bag as possible. And here, the invariant perspective maybe stops right here. Right? I think with a little bit of experience, you'll be able to tell the eigenfunctions of this method. But without that extra experience, you know, we could tell one, but not anymore. So the geometric, if you will, approach, the invariant approach stalls right there. But the algebraic perspective has no problem. So let's discover. This is a wonderful example for not knowing the answer when treating the objects on their own terms. So now we'll resort to picking a basis. In my classroom, I try several different bases. And we relearn the lesson that the matrix is always different, but the eigenvalues are always the same. And, but right now we'll just choose one. And then you can find, I have more exercises. You can find other bases where you can check your answer again. But let's just choose the most boring basis there is, which consists of 1, x, and x squared. Once again, we're limiting our attention to quadratic polynomials. If we broaden our attention to cubic polynomials, I'd have to throw an x cubed. Is this a good basis? Almost never, right? In fact, for the purposes of representing functions that typically occur in engineering or physical or geometric applications, this is just about, especially if you continue x cubed is x to the fourth and so forth, this is just about the worst basis you can pick. You can think about why that is. Why is this not a great basis, but this is not a good basis? But for our purposes, it'll suffice. Again, not convenient is a better word, or not effective from a certain point of view. There are no absolutes when it comes to choosing bases. Okay, but let's just operate in this basis. If this basis is good for one thing, it's for decomposition with respect to this basis. Nothing. If you have a polynomial, somebody just gives you a polynomial, and you have to decompose it with respect to this basis. That's a cinch. So there is no argument there. From that perspective, this is perhaps the most convenient basis. Okay, let's represent dilation. with respect to our basis. Let's call these functions, what would be a good name? That's the letter we haven't used yet. b1 of x, b2 of x, b3 of x. So d sub b equals... Okay, I need to leave enough space for actually determining the eigenvalues and eigenvectors of this matrix. So we can find out the eigenvalues and eigenfunctions of the transformation from which it came. Hopefully this will be enough space. Okay, so this column db1, this column will represent db2, and this column will represent db3. Okay, so what is... better write it down. D of B1 is, if we discovered, of course, is 1. Decomposing 1 with respect to this basis gives us 1, 0, 0. And you should begin to see how there's something wonderful about the algebraic perspective, because no matter what the real life example looks like, whether it's geometric vectors or functions or maybe vectors in Rn to begin with, the representation always has the same fabric. It's just a set of numbers. So there's some great standardization going on there. Now you have whatever the original problem is, and whatever basis you choose, the representation is just an n by n table of numbers. MATLAB is just sitting there waiting for it to, waiting for the matrix to come in so it can do its magic. Okay, x. Do we have x? Okay, so I'll just refer to this. So d of b2 is, well, actually we have all of them. I'm just duplicating my efforts. And d of b3 is 4x squared minus 4x plus 1. So let's just put these numbers in. So this number is, this vector or function has components minus 1, 2, minus 1, 2, minus 1, 2. And this one has components 1, minus 4, 4. 1, minus 4, 4. That's wonderful. Okay, so now we're ready to have our matrix and we're ready to analyze it. And the answer of eigenvalues and eigenfunctions for this obscure transformation, as obscure as the world is when your eyes are dilated after a medical exam. Sorry about that one. But the eigenvalues and eigenfunctions are about to be revealed. They're all in here. And it's not so hard to analyze this matrix. Had I chosen a different basis, maybe I would have gotten a matrix that's a little harder to analyze by hand. But MATLAB would have no problem with it. Okay, so our first, because it's a triangular matrix, our eigenvalues are on the diagonal. Are there 1, 2, and 4? So lambda 1 equals 1. The corresponding eigenvector is easy to see. V1 equals 1, 0, 0. And that's the eigenvector we know about right here. Alright, because let's call this P1 of x. P1 of x equals 1. The corresponding lambda 1 equals 1. That's the one we already knew. Let's discover one we didn't know. Lambda 2 equals 2. Lambda 2 equals 2. Now we have to do a little bit of work. I'll keep it small though, because it should be quite easy. So subtracting 2 from the diagonal, we get minus 1, 1, 0, 0, negative 4, 0, 0, 2. And you see that the corresponding eigenvector here, V2, is 1, minus 1, 0, which corresponds to the eigenfunction 1 minus x. 1 minus x. Maybe I'll write it as x minus 1, because after all I could have chosen minus 1, 1. X minus 1 sounds a little nicer. So, P2 of x equals x minus 1. So simple. Let's see if it actually works. What is x minus 1 under dilation? Well, the rule is plug in 2x minus 1 for x. So plugging in 2x minus 1, we get 2x minus 2. Hey, we find out that d of p2 is 2x minus 2, which is indeed 2 times x minus 1. I don't know about you, but I couldn't guess it. That x minus 1 works, and lambda 2 is the corresponding, lambda 2 equals 2 is the corresponding eigenvalue. So it's really a glorious moment where you see the power of algebraic methods. Before we saw the power of geometric methods, but what we're really seeing is the power of the combination of geometric insight or invariant insight and algebraic methods ready to do their own thing no matter where the problem came from. Can you guess the third eigenfunction from this? I think once you see the third one, you would know what happens in the cubic case if we extended this to cubic polynomials and higher order polynomials. But let's just see. Let's not try to guess. Let's turn off our intuition and let the algebraic method carry us through. So, lambda 4 equals 4. Subtracting 4 from the diagonal, we get minus 3, minus 1, 1, 0, minus 2, minus 4, and 0, 0, 0. Once again, a singular matrix. Here's how you determine the null space. We talked a lot about this in class. You really shouldn't do row-reduced echelon form and Gauss elimination too often. With these matrices, it's very easy to determine the null space. The third entry is taken care of. So by just looking at the second entry, it's clear that we have to take these two columns in proportion of minus 1, minus 2, 1. And having taken them in proportion minus 2, 1, let's see what we have to do for the first entry. We already have 2 plus 1. That's 3. So we just have to take 1 of the first column. So the null space is 1 minus 2, 1. Let's go straight for what polynomial this represents. It represents x squared minus 2x plus 1. That's P3. X squared minus 2x plus 1. Out of space. Let's see. Do you see why it works? As I'm writing it down? X squared minus 2x plus 1. That's what our algebra work is telling us. P3 of x equals x squared minus 2x plus 1. So the claim is that under dilation, this becomes 4x squared minus 8x plus 4, because this corresponds to the eigenvalue 4. Is it easy to see? It actually is. It's not easy to see when it's in this form, but if you were to rewrite this, which is what it is, x minus 1 squared, now it's easy to see because x minus 1 becomes 2x minus 2. 2 comes out from the parentheses with a square, so 4 times x minus 1 squared. So it does indeed become 4. And you see all of these actually follow the same pattern. This is x minus 1 squared. This is x minus 1 to the first. And this is x minus 1 to the 0. And it's now you can see what happens in the cubic case. And now you can come back to the invariant interpretation and say, well, of course I see what's going on now. What's going on now is that my eigenvalues are 1, 2, 4, 8, 16, 32, and so forth. And the corresponding eigenvectors are, eigenfunctions are 1, x minus 1, x minus 1 squared, x minus 1 cubed, and so forth. And now, so much structure is revealed. But how? By letting the algebraic method take over. Do the hard work, which is quite robust. We were able to do it by hand. If we couldn't do it by hand, MATLAB would do it for us. we obtain, these are the eigenfunctions, almost. These are not the eigenfunctions themselves. These are their components. These are the components of the eigenfunctions. And it's really, so this was a case where, from the invariant perspective, we couldn't tell much, but the algebraic perspective worked just as well. So it's the combination of both. A good exercise for you right now would be to choose a different basis and obtain a matrix. You will see with a different basis it'll be a completely different matrix. But its eigenvalues will still be 1, 2, and 4, so you don't have to look for them, you know what they are, but find the corresponding eigenvectors. And then when you know the eigenvalues, eigenvectors are simple, it's just a question of the null space. It's finding the eigenvalues that could be difficult. Okay? And then make sure that the invariant answers are consistent with what we obtained here. So this is the second example, and this almost completes today's topic, which is matrix representation of linear transformations, which is the linear algebra way of saying, let's use very powerful algebraic methods for solving problems that are invariant, interesting on their terms, or even geometric. And when the geometry fails, algebra takes over. When the only way to keep algebra effective is to maintain the geometric perspective on what's going on. And linear algebra is the perfect subject for learning these ideas. And then later on, I hope you move on to my tensor calculus lectures. They are really, tensor calculus is really the ultimate language for what linear algebra does for things that are straight and linear. Tensor calculus does for things that are curved, non-linear, curved, not straight, in 3 dimensions and higher dimensions as well. The number of dimensions is not so important, but it's this generality. And in linear algebra, we've really emphasized our freedom in choosing whatever basis we want, whatever basis the problem dictates, and try to do as much as possible without a specific choice of basis, but in a general basis. We'll follow this up with a little discussion that will happen with respect to a general basis, where I'll explain why it's this matrix and no other that represents the linear transformation. So when you move on to curved spaces, you can no longer introduce a basis and represent the entire space. You need to introduce a point-wide coordinate system to capture the entire space algebraically. But the philosophy, the fundamental ideas of arbitrariness and maintaining the geometric perspective and combining algebra and geometry certainly carry on. Thank you very much. I really enjoyed this.